Welcome back. Let's do another Thevenin equivalent circuit. We are given this little circuit right here with an 80 volt source and a resistor network. And then terminals AB are terminals of interest for the Thevenin equivalent. AB. We have a 10 ohm resistor, a 2.5 ohm resistor, and a 30 ohm resistor. This is what's given. Okay, this circuit is given, and we want to find the Thevenin equivalent. So for this method, we're going to use a two-step process. So there's step 1 and then there's step 2. Step 1, you want to find V sub Thevenin, and that's kind of like a separate little problem all by itself. And then when you're all done with that, we want to solve for R sub Thevenin. So the point I'm trying to make is don't mix these two up. Don't use values that you find in like halfway through this first process. Don't use those values kind of in the middle of the second process. You know, the final answers are good, but the values in the middle, you know, don't mix them up, all right? So step 1 here, we're trying to find what is V Thevenin. So V Thevenin is, oh, made that look like it's connected. It's not connected. Whoops. Ignore this line right here. So V Thevenin is just, it's just this. It's just the voltage across AB here. So let's redraw that so I don't mess up the original circuit too much. You know, although I'm not going to change it a whole. But here's the change I'm going to make. Look. So when there's no load connected across AB, right? When there's no load across AB, there'll be no current in here. This I will be equal to 0. And if I is equal to 0, then there's no voltage drop across the 2.5 ohm resistor. In other words, this 2.5 ohm resistor is behaving as if it were not there. So I'm going to draw with a dotted line. And I'll even write out here to be clear. There's no current or voltage across the 2.5 ohm resistor. So you can sort of pretend that it's not there. And if you do that, then this just becomes a voltage division problem. All right? So now we can use voltage division. So just a little trick, kind of nature of circuits, the behavior of circuits that we can do. So basically, so this is V sub Thevenin with this polarity here. How do I know the polarity? I guess I'm just choosing it, really. I'm sort of choosing it. I'm choosing it up here, kind of. And I mean, the final circuit will have the appropriate behavior with reference to this sort of arbitrary polarity, I guess. Yeah, so V sub Thevenin is given by voltage division for this particular problem. So, you know, we're doing step 1 here. We're solving for V sub Thevenin. And it just happens, it just so happens that voltage division will work for this particular problem. Generally speaking, you still have the 2 steps. It's just you'll use different methodology for each of these 2 big steps here, right? So here voltage division works. So basically this 80 volts is being divided across the 10 ohm and the 30 ohm, right? This 80 volts, some is being dropped across here and some is being dropped across here. And this drop across here is just coming out on these 2 lines is the same voltage that you're going to see at AB, because there's no voltage drop in this 2.5 ohm resistor, because there's no current in the 2.5 ohm resistor. All right, that's the whole problem in a nutshell. So voltage division, you put both resistors on the denominator, and then the voltage of interest you put on the numerator. That's 30. So that's the equation. The voltage division equation works out to be 60 volts, which means, let's just do a double check on that, which means there's 60 volts across here, so there must be 20 volts across here to sum to 80 volts. And if there were 20 volts and 60 volts, that's a 3-to-1 ratio, which corresponds to the resistor ratio of 10 to 30. Okay, so 10 to 30 is a 3-to-1 ratio, and 20 volts to 60 volts is a 3-to-1 ratio. So it looks good. So that's V sub Thevenin. That was step one. So we happen to use, voltage division will work in this particular circuit because of just the way it works out. We'll see some other methodology. But anyway, that was step one. Now you kind of start over with R sub Thevenin, all right? So R sub Thevenin is another problem. And here we're going to, we have a variety of methods we could use. We don't have any dependent sources. That is, we don't have any diamonds. We only have circles. So when you only have circles, you can use the open eyes, short V's method, and then followed by resistor simplification. Okay, that happens when you have only these guys. So we do that. We open the eyes and we short the V's. So there are no eyes. There's no current sources in here. What I mean by open the eyes, I mean current sources. Replace them with an open circuit. And short the V's. By V's, I mean voltage sources. We have a voltage source, so we can short it. So I'm going to short that guy. So this guy here, he's gone. He's shorted out. This 80 volt guy right here, just short him out. We're just using the method. We're not talking about why it works here. We're just, we're just going to use it. So this 2.5 guy comes back. And that's what I mean by this is two separate problems. Don't apply anything that, you applied in the first problem. Okay? So we're starting over with the original circuit here, and we're using this methodology on the original circuit. And this methodology says, well, when you only have these circles, that is, when you only have dependent sources, you can open the current sources and short the voltage sources. And then you can use resistor simplification. That's the method for finding R sub Thevenin. That's one of our methods for finding R sub Thevenin. And it works when you only have the little circles. So resistor simplification, this guy here, we just want the equivalent resistor seen from terminals AB. So R sub Thevenin is the equivalent resistance seen from AB, and that would just be, these two guys are in parallel, you see? So the 10 is in parallel with 30, and that result is in series with the 2.5, right? So like, if you were looking at AB here, looking for the resistance, you'd have 2.5 volts, right? 2.5 ohms, and then you'd have the equivalent parallel, right? So it's 2.5 in series, and then the 10 and the 30 in parallel, and then back to B. So this works out to 10 ohms. So that's our Thevenin. This is R sub Thevenin. So our final circuit, okay, this is like our Thevenin equivalent circuit here. Is the last thing. The answer you get from step 1 is the voltage, and the answer you get from step 2 is the resistance, and you throw those guys together. This is V sub Thevenin is 60 volts, and this is 10 ohms. This is R sub Thevenin equals 10 ohms. That's the answer right here. Okay. Fairly straightforward problem. See you next time.